Okay, this second screencast in the series is based on getting the difference between mass and weight. This can be very tricky because we live on an Earth that constantly has that same gravitational field pulling on us, and so we tend to not distinguish between the two. We tend to treat them as one thing. In reality, they are two different concepts. Again, mass is a measure of the matter that makes up an object. And then a weight is a type of force. It's a pull. We often think of it as the pull of gravity. It's an interaction between the object and the gravitational field that it's present in. Alright, so to try to get some of the differences here, and number one, the standard metric unit for mass is the kilogram, kg. The gram is the base unit. We use the kilogram in physics because of the size of objects we use. And the standard metric unit for weight is a force unit, which is a newton. So a kilogram, again, is kilogram, and that means 1,000 grams. And measures how much stuff you're made of. And then the N stands for the newton, which is the unit of force. After all, Newton's laws of motion are all about force in the international system. Now, an object's mass, again, refers to the amount of stuff present in the object, so this is d, and an object's weight refers to the force of gravitational attraction. Now, it could be to the Earth. If you were on a different planet, we could have your weight on that particular planet. Weight is the force of the gravitational attraction to whatever is creating the gravitational field you are currently in. Depending on your location, that could be multiple objects creating an overall gravitational field that you would make your weight compared to. In terms of the table, in terms of the relationship, the gravitational force field at the surface of the Earth is 9.8 newtons of force, newtons of weight, for every 1 kilogram of mass. And oftentimes we will round that to 10 newtons per kilogram for simplicity, if it's within a good enough percentage for what we're trying to do. In this case, we're going to just round it off to the 10. So if I have a melon that has a mass of 1 kilogram, for every 1 kilogram of melon, I will have 10 newtons of force. So the approximate weight or pull will be 10 newtons on the object. An apple that has a weight of about 1 newton, okay, 1 newton, and it's 10 newtons for every kilogram, would have a mass of about 0.1 kilograms. 0.1 times 10 would get me to the 1 newton. Pat here has a mass of 25 kilograms, then 25 kilograms times 10 newtons per kilogram would give us, on the surface of the Earth, a weight of approximately 250 newtons. Okay, so the relationship is always a factor of 9.8, larger or smaller, and it is often rounded to 10, and it is based on the gravitational field strength of the Earth at its surface. If you move out into space, into orbit, that's going to change somewhat. If you are going to the moon, that's going to change to a totally different value. It's only good here at the surface of the Earth. Okay, so we're going to get a spring scale. We're going to actually start weighing things. If we have a 1 kilogram mass, that would be about 10 newtons. If we have a mass of 5 kilograms, then again, for every 1 kilogram, we're going to have about 10 newtons. So 5 times 10 is going to get me a weight of approximately 50 newtons on my scale. This picture here refers to the first one, the 10 newtons. If we have 70 kilograms, then we're going to multiply that by 10 newtons per kilogram, and we'll be at 700 newtons. Okay, so in the English system, if it's 32 feet per second, per second, then just like 9.8 meters per second squared is the acceleration due to gravity in the international system, and that's 9.8 newtons per kilogram, we'll have 32 pounds of force for every one slug. So if you weighed, say, 96 pounds and you had 32 pounds for every slug, then 96 divided by 32, you would be 3 slugs. Now, that's just to show the way this kind of process works. We're not going to work in pounds and slugs, but if you get into engineering, sometimes you do end up working in English units, and it's the pound and the slug, which is a very uncommon everyday used unit. 6, you might be wondering about your metric weight. So if you're trying to figure out how much you weigh in, say, newtons, which again is not commonly done, but can be figured out, there's 1 newton is equal to every 0.22 pounds. So if you weigh 100 pounds, then if you multiply that by 1 newton for every 0.22 pounds, then you will have a weight in newtons of 455 newtons. Now, even in the rest of the world where the international system is commonly used, in typical everyday usage, they don't really talk in terms of newtons. Nobody says, I weigh this many newtons. If you watch any international sports, they're always talking about the players in terms of how many kilos, in other words, how many kilograms of mass they have. It's just, you don't buy food by the newton typically, you would buy it by the kilo. So, interesting enough, there's a case where even in countries that use this international system, they don't really use the newton as an everyday kind of usage. Okay, so the mass and weight of an object, 10 kilograms on the Earth. If it has a weight of 10, if it has a mass of 10 kilograms, so 10 kilograms is the mass, then we would multiply by 10 newtons per kilogram, or 9.8, and we would end up with approximately 100 newtons worth of force, 10 times 10. Now, if we take it to the moon, where gravity is only 1/6 as much as it is on the Earth, then what we'll have is the mass, the amount of matter it's made of, will still be the same. This will still be 10 kilograms. Unless we cut the object into smaller pieces, take some stuff away from the object, or glue on some additional matter, the amount of mass stays the same no matter where you're located. It's the weight that'll be different. The moon has a smaller gravitational field than the Earth. In fact, it's about 1/6 that of the Earth. So that makes its acceleration rate and its force field about 1.7 newtons for every kilogram. So on the moon, it would be 1.7 times 10, and you would only be about 17 newtons of actual force pulling on you. So you would weigh a lot less than you would on the Earth. It would be easier to jump, easier to stay in the air for a longer period of time if you were on the moon than if you were on the Earth. Okay, so again, the conclusion we can draw from that is that the mass of an object is independent, does not depend upon its location in space. Mass is the amount of matter you're made of. We just need to count the number of atoms and how much stuff is in each of those atoms. Don't need to know what the gravitational field around you is like. If we find the gravitational field, the force in newtons, then we're talking about the weight. Again, here on the Earth, those are easily switched around. It's hard to differentiate between the two because we live in a place where that gravitational field is always constant.